The rest of this week is going to be spent on the topic of descriptive statistics. And so I've got a series of videos that will walk us through how do we characterize all of these things, the distribution, the shape, the center, the position, the spread, and the skewness. Now, before we get into this, let me just mention that you're probably going to find this to be pretty easy because you've seen a lot of this before. So chances are you ran into means and medians and modes back in grade school even. Anybody who took a high school stats class would have run into variances and standard deviations and percentiles, and we're kind of surrounded by this stuff. With that said, the way that it gets covered doesn't always get at all the nuances that you really need to use it well. And I think that this is probably the most useful, some of the most useful tools that you'll get out of the class, because these are going to be the things that you use every day. Anytime you get a data set, the first thing you have to do is to make sure that the data is okay, and you do that through descriptive statistics. So let's start with distributions. Now, usually the techniques get divided up by the type of variable that you're studying. So there are two broad types of variables. There are categorical variables and there are numerical variables. So categorical variables are things like color, so red, green, yellow, blue, marital status, married, divorced, widow, single, other, gender, those would all be examples of categorical variables. We have some descriptive statistics that are mostly designed for those. We have many, many more descriptive statistics for numerical variables, like your age or the diameter of a part. So you get all of one slide on categorical variables. We're going to be studying a real data set that I have from a fitness club. So the fitness club attracted many members. So you think about your unit is a member. And one of the attributes that was measured was, how do people pay their bill? Okay, so for example, you can pay it with a book method, where they give you a coupon book and you pull out a coupon every month, write a check, send in the check with the coupon. This data set's a little bit old. In the olden days, we did that sort of stuff. There's also a statement method where they send you a statement every month and you mail in a check. Then there were two EFT methods. So EFT means electronic fund transfer. So you could either give them your credit card number, or you could give them your checking account number with permission to debit you a certain amount every month to pay for the bill. All right, so this is an example of a categorical variable. So the question is, how do we summarize this? Well, in R, one way to summarize it is with the table command. So what table does, you can just use this on any variable. It just gives you counts. And so you can see you've got about 8,000 people who used the book method, about 5,000 who did statement, and so forth. So this is a way to summarize the these 20-odd thousand people in our data set and how they paid their bill. Now, I don't completely like just the table command, because it doesn't give us all the stuff that we're usually interested in. So I've written my own little command called freakdist. So freakdist is a function. You can copy and paste this into R, and so that you'll have your own freakdist function. So what freakdist also does is it computes the percentages, and then it computes the cumulative counts and cumulative percentages, which are the things that we're usually interested in when we compute a frequency distribution. All right. There's also a set of visual displays that we can use. So the way we do this in R is, well, let me pause, back up for a second. I'm going to give you a quick history of graphics in R. So there have been at least 3 generations of graphics functions in R. So there's the original set of graphics routines, which were developed for the S language. This is way back in the 1970s, late 1970s. And those functions tend to be, simple but very good for the basic things. Now, obviously, they don't do everything. Otherwise, there wouldn't have been subsequent generations. And what happened next was that in the late 80s and early 90s, a scholar by the name of William Cleveland, devoted his research to developing graphical tools. And he did all of this work in the language S, which is a predecessor to R. And he developed something called the trellis library, which is called lattice in R. Maybe there was a copyright problem, I don't know. And he developed a lot of really innovative tools for helping us visualize data. Then later on, Hadley Wickham came along and developed the 3rd generation of graphics in R, which is called ggplot, the grammar of graphics routines. I think we can skip the 2nd generation, but the 1st and the 3rd generations are going to be very useful to us in class. So I hate to throw both of them at you, but there are certain things that are just a lot easier to do using the base R fundamental graphics routines. Other things that are much easier in ggplot. All right, so that was a bit of a long-winded explanation, but how do we make a bar graph? Well, there's a command in base R called bar plot, and you pass it the output from table, and you end up with, here's your bar plot. Here's the equivalent command if you want to use ggplot. So in some ways, this may be a little bit more complicated than the original one. To use this, you have to do an install. So you would say install.packages ggplot2. And then whenever you want to use it, you have to type library ggplot. And that loads the all the functions for ggplot into your R session. Now, you only have to type library once during a session. So if I'm doing a bunch of stuff, I'll just put the library commands at the beginning. All right, couple minor details about this. We usually insert a little bit of space between our bars as a visual cue to the viewer that these are categories and not a continuum. A couple other minor details about this. The areas, the lengths, and the heights of the bar all represent either the counts or the percents. Okay, so the area is proportional to the counts. The length of the bars would be proportional to the counts. The position of the end of the bar along this common scale is also a representation of the number. So we're taking all the numbers in a frequency distribution and encoding them with these graphical devices to help us make sense of it. So it looks like bars are more common than statement or the EFT methods. Sorry, the book method is more common. That's all I want to say about categorical variables. Let's move on to numerical variables. So I have a survey from a restaurant that asked its patrons, please rate your overall experience on a 1 to 5 scale. So 1 is poor, all the way through 5 is excellent. So how do we summarize a numerical variable? Well, it starts with a frequency distribution, same place that categorical variables started. And so I just ran my freq dist command and got this frequency distribution over here. But we also have a lot of other measures that we can be using, like the mean, the standard deviation, and so forth, that we'll be talking about in subsequent videos. Another thing that we can do is generate a histogram. So a histogram's similar to a bar plot, but a couple details are different. So number one, we get rid of the vertical space between the bars to signal that this is a continuum. Another thing that's really important about histograms is that the only thing we interpret with a histogram is area. Okay, so the area under these bars is proportional to the percents. We don't really interpret the height or the position along a common scale the way we did with a bar chart. So in this case, all of the bars have the same width. That doesn't have to be the case with histograms. So it's valid to have histograms that don't have bars of the same width. So because the widths are the same, the lengths are also proportional in this case to the counts. But in general, you should only count on using area. This is going to be kind of a foreshadow what we do with probability. So when we compute the probability under a PDF, we evaluate that probability by computing the area under the curve. We don't look at the height of the curve. So it's just a good practice to get into now to focus on interpreting area. All right. I've included a kind of a more detailed example of a frequency distribution. So this comes from the National Crime Survey the U.S. government did, and it's a frequency distribution to the question, what is your age? And so this was, I think, meant to be on adults. You can see some 14-year-olds and 15-year-olds completing this. I suspect the parents just turned the survey over to the kids and let the kids do it or something. This summarizes in great detail the age of our 18,000, 19,000 respondents. All right. I suspect that you've had a lot of exposure to frequency distributions in the past. If you haven't, I've written out detailed descriptions. So the only thing I'm going to do in this short video is a couple of the your turns. So the reason I do this is I want to get us into some habits that we're going to be using when we get to probability theory. And I suspect a lot of these, you've already done some of these things, but I want you to make the connection between what we're doing with probability theory and what we're doing with these descriptive statistics. So one of the questions that we could get asked is something like this. What percentage of people who took this survey are 40 or younger? Now, we're going to answer that question using the cumulative percent column. Now, you probably remember doing something like this with normal tables. Probably still use tables, where you went, and so what we're doing now is something completely similar to what you do with a normal table, but this is you can think of this as not assuming a normal distribution. In fact, in a minute we're going to see this distribution is not normal; it's somewhat skewed. But the way we answer that question is we just go to the cumulative percent, and we can just read off the answer. So the proportion of people who are 40 or younger would be 42.1%. Alternatively, we'd add up all these percents, and the sum of all these percents would give us 42.1. I'm going to go over to the scratch pad for a second, and I'm going to use some mathematical notation that's going to look somewhat familiar to you. So if I go over to my document camera, let's say that age is equal to the age of our respondent. So the way you would probably write this back when you were using your normal tables is, what's the probability that A is less than or equal to 40? And so what we saw from our frequency distribution was the answer was 0.421. And so that's just the notation that we're going to be using. All right, let's go back to the course packet, and I'm going to look at the next problem that I gave for you. Actually, we're going to skip over part 2. You can read the answer on your own. But another type of question that I could ask you is, what percentage of people are 65 or older? So let's go back to my document camera. And the way we would write this is, what's the probability or the proportion of people who are greater than, whose age is greater than or equal to 65? So we could just go add up the individual percents. That would be like adding up the individual probabilities from a probability mass distribution, PMF. But I want you to get in the habit of using the complementary rule. So what was the complementary rule? This is equal to 1 minus the probability that age is less than 65, strictly less than 65. And so we can go look that up now in our table. So if we go back, since we have, binned values of age, so I don't measure age to, many decimals of accuracy. I only have, integer values. The probability that you have age less than or equal to 64 or less than 65 is 84.1%. So I'm going to go write that down here. So this would be 1 minus 0.841, which is equal to then, what would that be? 0.159 would be the answer to this question. All right. Well, let's go look at the next question. The next question is, what percentage of people are between the ages of 40 and 60? So let's go write this out. What is the probability that A is between 40 and 60? So again, we could just go right out. This is just the probability that A is equal to 40 plus all the way through the probability that A is equal to 60, but we don't want to do that. Instead, there's an easier way. I call this a slice. We're going to take a slice of the distribution. This is going to be equal to the probability that your age is less than or equal to 60. But notice I've included too many people in this because I've got all the people under 40. So we're going to subtract off the probability that age is less than, strictly less than 40. So now I can go use my cumulative column. So the cumulative column in this frequency distribution is just like the CDF, the cumulative distribution function, in a probability table. So let's go look that up. So the probability that you are 60 or younger is given to us right here. It's 0.791. I'm going to go write that down before I forget it. We'll flip over to the document camera in a second. What's the probability that you're under 40? Well, the probability that you're under 40 is 0.392 right here. So let's go back to the document camera and you can see what I just did. So I wrote those two numbers out, and you can compute the difference and you have your answer to the question. So I know this is probably very basic for most of you, but it's extremely important that you learn those three skills. So whenever you have a less than question, so the first one was a less than question, you go straight to your CDF, and the CDF gives you the answer. Whenever you have a greater than question, like this one, you take 1 minus the CDF and you have your answer. Whenever you have a slice question about probabilities or percentages, then what you do is you subtract the larger from the smaller, and you're done. All right, so that's it for frequency distributions. Let's go look at some histograms of this. So this is a picture of the age distribution. And so remember, we interpret area. There's more area in the smaller values than in the larger values, indicating that there's a lot more people kind of in this 30 to 60 range than there are in the 60 plus range of this distribution, because the area is smaller. How did we create this histogram? So in the case of this restaurant example, I use the restaurant example first because it's so simple. I only had 5 possible values for my variable, and I could just go create bars that were proportional, had areas proportional to those counts. When you have a numerical variable, and if I measured age down to the nearest second, it's conceivable that everybody in my sample would have a different age measured down to the nearest second or millisecond. Let's go even smaller. And so then I'd have a bunch of bars that all had height 1, and that wouldn't be very interesting. So what do we do? Well, we're going to create bins. This is a very important technique. You're going to run into it again. A lot of machine learning methods, like trees, are basically based on forming bins. So what's a bin? So bin is just some grouping of my age values. So I could group age into the values under 20, then 20 to 24, 25 to 29, 30 to 34, and so forth. Those would be bins. Then what I do is I count the number of people in each bin. Now, there's a little bit of a problem that we have with this. You have to choose the size of your bin. So the more bins that you have, so for example, if I were to make my bins 20 to 40, 40 to 60, 60 to 90, this would be my histogram. If I made my bins every 5 years, this would be my histogram. If I had 40 bins, this would be the histogram. 80 bins, this would be the histogram. So how many bins do I need? How many bins do I need? So the software usually does a pretty good job of choosing some bins for you, but that doesn't really answer the question. How many bins do you need? Well, here's my answer. I would say that we've gone overboard with this last histogram here. We have too many bins. Reason for that is the histogram's a bit jagged. So when we look at this, we see a spike for this particular age, whatever that is. And I don't think that spike is real. So what do I mean by real? If I'd drawn a different sample of people, would I still have that spike of people at that age? And the answer is probably not. This is just an artifact of the sample I happen to have. Likewise, there's some dips. I have a dip here. I don't think that dip is real. It's just an artifact of the sample. So I don't want my histogram to be displaying just artifacts of my sample. And so I'm following the noise in the sample is a term that we're going to be using by having so many bins. This is just, my bins are too small. So I would say this 20 bin solution is probably a pretty good picture, because if I had drawn a different sample of data, I would have, I don't have any of those dips or the jags that show up down here. And so this would be robust across my samples. All my samples would show that same basic shape. Now, you can go too far, and I would say that going down to 5 bins is a bit too few. So, whether you do 20 bins, you start to see some dips that may not be real with 40 bins. I think the 20 bin solution is pretty good. All right, so that's how we make a histogram. We start out by forming bins. We compute the frequency in each bin, then we make our bars proportional so that the area is proportional to the counts. One more example. Well, actually, before I do that example, I'm just going to mention a term. The shape of this distribution is said to be right skewed. So what do I mean by right skewed? What I mean is that there's a bit of a long right tail. Okay, so this tail to the right-hand side is longer than the tail to the left-hand side. And so we would call this a right skewed distribution. The way I always keep track of this is where's the long tail? If it's on the right-hand side, it's a right skewed distribution. If it's on the left tail, it would be left skewed. So we had an example of a left skewed distribution earlier. Let's go back and look at that. This would be a left skewed distribution because the tail is on the left-hand side. So just a little bit of language that you need to have to discuss distributions. One more example in this module on shapes of distributions. The example is kind of a famous one. It gets used in a lot of statistics books. This comes from a geyser at Old Faithful National Park. Sorry, at Yellowstone National Park, and the geyser is called Old Faithful. So what we have here is the lengths of eruptions. This is a geyser that shoots water from the ground. And we've measured about 100 of these eruptions. So in this case, my unit of analysis is an eruption. And I'm measuring how long this eruption was in minutes. And so this is a histogram of the eruption length. And so when we look at this, we see two modes. And so there's, these correspond to, if you will, types of eruptions. And so what I would conclude from this is some eruptions are short in that they only last about, a little bit less than 2 minutes or so, while other eruptions are longer in that they last about 4 minutes or so. Another conclusion that I would make from this is that the long eruptions are more common. So why do I conclude that? Well, the area of this local mode is substantially greater than the area of this mode. So if I were to go to Yellowstone National Park and witness one eruption, chances are it would be a long one, but there's a substantial probability that it would also be a short one. Now, there are a few other points that you can make about this. The starting point of the bin will change the look of the histogram. So the only difference between this histogram and this histogram is here I started my bins at 1.5. Here I started them at 1.25. In both cases, the bin width is a half a minute. And so the histogram looks a little bit different. It's a bit of a problem that the shape of the histogram can change a little bit. I mean, it's still bimodal down here. A different way to do this is to have a moving bin, okay, where you can think about a sliding window that I use to determine the height of this curve. And that's the basic idea of a non-parametric density estimate. So this is an example of a non-parametric density estimate. Just for kind of illustration purposes, I'm going to flip over to R now and show you how we can get these. So let's go read in our data. You can download this from Canvas if you want. The hist command is the base R command for looking at a histogram. Here's the default version, which I think looks pretty good. The way to get a non-parametric density estimate using old-fashioned base R is you plot the density function of the data set. So here's our nonparametric density estimate, and I think that looks really good. Now, just to kind of introduce you to ggplot, here's the ggplot version of it. I'm gonna make a data frame out of this, and then this means I'm gonna send that data frame to the ggplot function. And AES stands for aesthetic. And so this is just going to define what is the variable I'm studying. So the variable I'm studying is x, which is what I called my measurements up here. Now I've defined what variable I'm studying. What do I want to do with it? Well, I want to make a histogram out of it. So geom histogram, so the plus sign sends this, this to this plotting function, and then I can specify various arguments like the number of bins that I want. So let's just go see what this looks like. This is the ggplot version of the histogram. Now, instead of sending it to a histogram, I could send it to the geom density function, and I get a nonparametric density estimate of the same thing. So that just gives you a really short introduction to what I call the first and third generation graphics functions in R. Okay, so that concludes our discussion of frequency distributions and histograms, density estimates. You should go try some problems on your own. I know this has been fast, but I'm assuming you've seen a lot of this material in some of your previous courses.